Hi and welcome to another Hopper internals video. If you don't know what Hopper is, then you shouldn't be watching the internals videos yet. You should, go back to playlists and take a look at some of the more general videos on Hopper. I'm going to specifically walk through how I ported the Hopper runtime to the Raspberry Pi Pico in this video, and why I'm confident that in the future, this was a quick and dirty port in a very portable way. So obviously performance is a bit of an issue, but I hope through this video to illustrate why I'm confident that it has incredible potential for the future. So I'm going to use a specific example to show this as well. So let's go back to that example. I'll get rid of our blinky light here. Let's break the debugger, get out of there. So the sample I've been using for illustration for performance is this Fibonacci sequence sample that I found online. I guess I've got the URL in here where I found it. Just because I'm not much of a Python guy, so I needed to find someone else's timing for a Python example, and this Fibonacci sequence was a good one. And another reason it was a good one was because it stretched the boundaries of the runtime call stack, because it's recursive, and got me to improve the general performance of the call stack across everything for this example. So let's build this. So it does Fibonacci 424, and the result should be this number over here. Let's load it into the debugger. We're now in the debugger. And now I'll run it without the debugger. So you can run in the debugger either with debugging or without. So if you run without debugging, it's a bit faster. So let's run that. So while this runs, this takes a while to run. Right now it's running in 14 seconds. I've seen it run as fast as 10 seconds. The guy whose sample I nicked on the internet, he had it running in 2 seconds in MicroPython. So 14 seconds here or 15 seconds here is 7 times slower than MicroPython. So that's our starting point here for now. Slight advantage we have over MicroPython is if we start debugging into this reset and start. It's kind of tricky to do this with MicroPython. You can't symbolically debug. Let me switch screens here so you can see what's going on in the debugger. Here we go. So call stack on the right, local variables, global variables, arguments, step into the Fibonacci sequence function. There we are. Step recursively into another, and you can just see the call stack going nuts here. Anyway, you can't easily do this or break, controls to break. Where am I? Still in the stack sequence, obviously. Let's put a breakpoint on. Let's break again. Oh yes, I'm having difficulty breaking because it's in quite a tight loop. So I'm just going to restart. That does happen occasionally. So there we go. Let's fade back and fade back. We're back again. All right. Enough of that. It's difficult to break the debugger out of a tight loop where I only check for breaks. I don't check for breaks all the time. I check on like function returns, for example. Well, if you just continue to call recursively, it might not return for a while. Anyway, let me show you how I ported the runtime. So, and yeah, the starting point was that Fibonacci sequence takes 14 seconds, which is a little slow. It's 7 times slower than MicroPython, and obviously we'd like to be faster than MicroPython. So this is the runtime that I wrote in Hopper. So the runtime on Windows is written in C#. The runtime on the 6502 is written in 6502 assembly. But I wanted to make it a bit easier to write future runtimes. Excuse me. So I wrote the runtime in Hopper. Tricky thing is that the runtime relies on a heap manager and garbage collection. And that's quite a lot of code to write. So to get it to cross-compile it to C, so I wrote a cross-compiler which adds to the tool chain. So let's just do this. This is my batch command to build the runtime. So the steps in the tool chain are preprocess, compile, which is the Hopper compiler. It generates some intermediate format. I've then got an optimizer, a full program optimizer, which will optimize the intermediate format. Does stuff like dead code removal, etc. So it and inlining. So it actually inlined these, and then it's got a code generator, and the code generator generates the Hopper binaries, and the Hopper binaries are Hopper opcodes that get interpreted by the Hopper runtime. I added a new step to the tool chain called cgen, and what cgen does is it goes through the Hopper binary, Hopper runtime, the Hopper opcode binary, and converts it to C code. So it's a very shallow port to do it that way, to do it instruction by instruction, just convert it to C. And what you end up with is very ugly C. I can demonstrate quickly. So let's have a look at what the C looks like. Are we on the right screen? I believe we are. So the Hopper runtime C looks like this. If I zoom in on this, you'll get a better idea. So it's taking Hopper bytecode instructions and converting them into C. And it obviously has enough of a little library for the machine. So the machine itself is very simple. It's implemented with, so the machine basically has stack instructions. And then it has some, it's got reading and writing of a big chunk of memory somewhere. Yeah, some reading and writing of memory. And some platform stuff to use the platform longs, for example, 32-bit longs. And memory, so, and the serial port interface, yeah. So all written in that. But you end up with very badly written C code if you just basically cross-compile these bytecode instructions into C equivalents. Yeah, not so pretty. Let's edit the runtime again. Not checked, etc. Wondering why this doesn't look more inlined to me right now. It is inlined. So yeah, it inlines some of them as well, like that, like this return function. Very direct, no checking. Right, so I cross-compile this 7,000 line program that I've written, where I've re-implemented all of the Hopper library, like string APIs, for example. So if we have, append one string to another, it's all written by hand, character by character, rewritten in Hopper to implement the whole Hopper runtime. And the big things were the string library, dictionaries, which include hashes. So you can have, for dictionaries, you can have keys which are hashes or keys which are value types like integers. It's got a hash, basically a hash table implementation, all written in Hopper. And I had to write this entire 7,000 line Hopper runtime without using reference types anywhere, because I can't cross-compile to a heap manager that doesn't exist. So I did it all with value types and with a big chunks of memory. So it's all much the same way it was written on the 6502. It's written as if it's just running on the metal. Okay, so once it's in here, how do I get it onto the Raspberry Pi Pico? Well, there's 30,000 lines here, that 7,000 lines of Hopper translated into about 30,000 lines of C. I then cut and paste that into our favorite non-IDE, which is this Raspberry, the Arduino IDE. So starting over here on line 500, I pasted in the C code that was generated by my cross-compiler. and it's, you know, almost 31,000 lines, well, 30,000 lines of C, and then I copy that across to the Raspberry Pi Pico, and that's how I get the runtime across. Well, and that's how it becomes 7 times slower than Python. So I thought, let's try an experiment. What happens if I cross-compile the Fibonacci sample directly to C, rather than cross-compiling the runtime and then running the Fibonacci in Hopper bytecodes on top of that runtime? In other words, what if we were running on the metal with the same cross-compiling? So let's try that. So let's go to my samples. So there are a couple of problems with this issue. So a couple of issues with it. So if I have a look at the Fibonacci sample, the first problem with it is that it uses the long type. So I can make this a bit bigger. Let's do that. Yeah, just got to remember to switch back. So it uses the long time type to do the timing, because it's for milliseconds, and then subtracting milliseconds and then dividing by the number of loops and outputting it. Second problem it uses is it uses strings. And strings are a heap type, and my cross-compiler only cross-compiles value types. So this is not going to cross-compile. So if I try to cross-compile it, let's try cgen with it. So cgen generates C from the Hopper opcodes. So let's do that. Fibonacci unsigned integer version. And it goes pop local copies not implemented. So that opcode is not implemented. And what that does is pop copy local. The heap manager on the Hopper runtime uses the stack as a live list. If something's not on the stack, it can't be accessed from anywhere. Therefore, it can be garbage collected. And it does a copy on assignment, which is effectively when it's popping it into a local or global variable. If you pop any that reference type, you're making a copy. So reference types are not implemented. The heap manager is not implemented in this cross-compiling tool, because you're cross-compiling to a platform where there's no heap manager. It doesn't exist. So that wouldn't work. So we'd have to butcher this example to make it work. So that's what I did with Fibo-lean here. So Fibonacci sequenced a lean version. So I got rid of the strings. There's no strings in there. And I've got this really painful way of writing out nice output. So to write out strings, I write them out one character at a time, because a character is a value type, not a reference type. So I can write out single characters at a time. I also implemented a way to write out integers without, because in the other code it would go int to string and then write out the string representation of the integer. But what I did is in Hopper I wrote some APIs that, where have I got that? Where I can show it quickly. Yes, in here. So I wrote out some APIs that walk through an integer and output it character by character. Here they are. So there's a write digit and there's a write int. And it's recursive so that it can go backwards through the string. Firstly, it puts out the sign if it's negative, and then recursively goes into itself, and then on the way back out again, the right digit is the recursive part, dividing by 10, taking the modulus every time, and then on the way back out the recursive loop, it pumps out the characters, and that's how you get them in the correct order from left to right. Otherwise, it would go right to left. Anyway, so short version, managed to get writing out of numbers done without using without using reference types either. The real problem that made this much more complicated was I still wanted to use milliseconds for timing, which is a long. So what I did is I sucked in from my platform port the implementation of long without really ever creating one. So I only use them inside emulated functions, and I'm not putting it on the stack in any meaningful way. I've just got this int here is the reference to my long, and then I've got two of them down here, subtracts one from the other, puts the result into there, does a division, and then I convert it to a uint before I print it. So but I had to include quite a lot of rubble to actually get to use long, and the externals I needed to use were these conversions to and from my new Hopper native, or my Hopper longs, which are the ones which are just a byte array of 4 bytes, to the native long, which is so that I can actually do arithmetic with it on the platform. Yeah, so it was quite a pain to do. But since I went to the trouble of importing all this rubble, I decided I might as well do blinky lights as well. So it means I've got these external functions to initialize the pin mode on the blinky light pin and switch it on and off, and I can delay 500 milliseconds. So I don't have a way of stopping this because there's no keyboard input, there's no serial other than output. So I just run the benchmark in a loop. I expect to see this output, and I turn the blinky light on and off for each loop, and I loop 500 milliseconds between each run of the benchmark. So we should see how that looks. This memory initialize, on the metal of the platform, I've just got a big chunk of memory, 64K, and I did need to, and all I've got is memory read and memory write of bytes and words. So let's go have a look at memory. Read and write of bytes and read and write of words, and then the initialization initializes something. It's not really a heap. It's really just implementations of malloc and free, as in the same malloc and free that you're familiar with from usual C. And I wrote these two functions back when I ported to the Z80 about 2 years ago. I wrote a runtime on the Z80, and I wrote this thing called Zopper, which was the first time I cross-compiled, and I cross-compiled at that point from the Hopper virtual machine instructions to Z80 assembler directly, and it was quite fast. So I had this free and allocate available, which were kind of handy. So this is how much work I had to do just to get this Fiberline to run. But it's worth it, you'll see. Anyway, so we have Fiberline there. So let's build Fiberline for the platform. All right. Now at the console, we run cgen on it. So we generate, so cgen Fiberline. So it now generated C code for this example. So now, before I forget, I should switch back to the desktop here. And we go back to Visual Studio. Let me make sure I'm on the right screen. Yes, I am. So I go to Visual Studio because in Visual Studio, I like to, because originally I tested this all on Windows, the C porting. But what I like to do here is let's include Fiberline's being included as the one I'm trying to build, and let's just build it. I do this to make sure it actually compiles before I go to the Arduino IDE, which is rather painful and slow. So now we'll go and we'll select this code that it cross-compiled. Now the runtime was, what was it, 30,000 lines? This is only 1,500 lines, which includes all the support material we needed. Let's go to the Arduino IDE. We paste in our Fiberline sample. So we went down from 30,000 to 2,000 lines of code total. Let's compile that and get it up onto our device. There we go. And it's flashing the Raspberry Pi. And we've flashed it. Now I'm going to switch back to the other view so we can see our, oh look, it's running, and it's running blinky lights. Why is it running so many blinky lights? I wonder. So how can we tell what's going on the Raspberry Pi? Well, in the shell folder, I have a sample program called terminal. Oops, thought it was in there. CD shell. And in the terminal example, all it's doing is running in a loop. It's connecting to the serial port, and it works with both the keyboard input and the serial port. So it looks for keyboard available, and it looks for serial port available. If it gets a character from the serial port, it simply prints it back to the screen, and it fixes line endings. That's all it does. So it's a tiny little loop that just fetches characters and prints them, but it also gives me a way to quit the Q key. So let's build that. And let's run term and see what's happening on our device. We'll connect to the serial port now. And our Pico is giving us results. It's running that Fibo sample once every 500 milliseconds. And the benchmark is taking 8 milliseconds. 8 milliseconds. Let that sink in for a second. So cross-compiled from Hopper bytecode opcodes to C, and then uploaded and running on the on the Pico is running at 8 milliseconds. So obviously dramatically faster than our 14 seconds that it took to run when it was running on top of the Hopper runtime, and faster than the 2 seconds that conventional MicroPython will take to run this example. And that's sort of the punchline of this, of why I am confident that a more serious port of the key parts of the runtime, specifically the part that executes the opcode and runs in tight circles, the inner loop, a port of that to just C, doesn't even have to be to, rather than using my cross-compiling tool to do the insincere port, actually hand-coding a port of the inner loop, I'm pretty sure that this is going to run blindingly fast once it is ported properly. But in the meantime, I'm quite happy with my existing port, because it only took me a few days to get it up and running. And I've got it running on other microcontrollers as well. I've got my favorite little Wemos D1 Mini. Let me see if I can get that in the view. This guy. So this is an ESP 8226 or whatever it is. So I've got it running on this device as well, just because to get it running on one device is easy, to get it running on multiple is a bit more tricky. But because it's so portable, you can just recompile and make it run anywhere now, anywhere that the C compiler is supported, and it requires very little support from the outside world to run. It's serial API and memory, malloc and free, basically. That's all it needs to get going. And then of course anything that you've got that's native, that's interesting, like reading and writing these pins. So what's next? I think based on how successfully fast it is to do this, I'm not going to worry about performance until I have much more functionality implemented. And the functionality I'd like to implement first is file support. So what do I mean by file support? If we just edit what do we got here? Yeah, if we go into the system, the Hopper system, it has a file and a directory unit, which does all the normal things you expect from a file API. A file exists, file deletes. It's got a nice way of having stable access to files called isValid. So after you've opened a file, to check for errors, did it open, did it close, did I have an IO error, whatever, you can just check, is this file valid? It also tells you, like, end of file, so keep reading from a file until it's not valid anymore, and then you've got to the end of the file. Read and write, read line, write line, appending either a byte or a string, etc. Timestamps, size of the file. So a good example of where this is used is in the directory command. Oh, directory, why did I get a question mark? Oh, let's do that. Huh? Right, if I give it a wrong example, I was trying to get help and it's not letting me put a question mark on the command line. So yeah, the directory command in Hopper. So if I look at the directory listing of the source, full paths, recursive. So that's, yeah, it's using the file API. Everything's using the file API. The editor's using the file API. So the first thing I'd like to port to the microcontrollers is a file system. So either using spiffs or using little fs. to take advantage of the flash on these little devices to put a file system on them. And at that point, then you can have a default program loaded in already, and when you boot into that. It's sort of an auto exec. Right now, if you turn the power off, your program goes away. So that's a good reason to build a file system first. And yes, I could just write it into the flash, but I'd like to do it properly and put it into the file system. So file system's the first thing. To do the file system, ideally I'd want to implement it using one of the serial APIs on one of these devices, so either SPI or I2C, and write the driver in Hopper. So the only thing that I want I could bit bang I2C or SPI, but I'd rather use the platform APIs for that because they exist on all the microcontrollers and they're nice and fast. So I'll build a unit to support those two different units, an SPI unit and an I2C unit, and then start building drivers on top of them. And the first driver to write will be the file system driver. The next obvious driver to write, which is going to make these things a lot more useful, and you can see the hint of it on the bottom of the screen right now, is the web driver. So HTTP client, a web server, a Wi-Fi interface, that sort of thing. And again, hopefully you can do that using the existing APIs and write the drivers in Hopper. I want as much of the code as possible to be written in Hopper because it makes it portable. It means that if we port it to a Raspberry Pi rather than a Raspberry Pi Pico, we don't have to rewrite all this stuff again. Anyway, a rather long internals video, but an interesting walkthrough of the state of where I am with supporting microcontrollers and why I'm confident that it's going to be really good once I get the final port done to these, or platform-specific ports done are going to be really good. Thank you for watching, and please give me some feedback.